Okay, so that's working now. So, hello, I'm Robin. I work at Intel's Network Platforms Group. And today, Aaron, Bhanu, and I are going to talk about OvS-DPDK. But it's not going to be about performance. There's plenty of sessions on tomorrow's agenda about the performance benefits of DPDK. Today, we're going to talk about enhancements that Red Hat, Intel, VMware, and others in the community have made to the code base to make it easier to install, deploy, configure, and use. OVS with DPDK has always offered great packet processing performance. But as the deployment and adoption in products continues to grow at pace, the ease of use has become equally important. And that's what we're going to cover today. So we'll start the presentation by looking back at last year's OVS conference and the co-located OvS-DPDK Design Summit. Here, members of the community met for a day to collaborate on the progression of OvS-DPDK. And there were a number of different topics covered, and one of them was usability. And in particular, this focused on what we as a community could do to address the statement in the install guide that the DPDK support of Open vSwitch is considered experimental. So this experimental tag should not and has not proved to be a deterrent in the adoption of this OvS-DPDK in products and deployments. But for the broad market, there's this underlying sentiment that the user space data path is that little bit trickier to use than the kernel data path. And if it's possible that we can make advancements to help to remove that experimental tag, that they be welcomed. So the outcome from this meetup last year was this list of items that's published on the mailing list that we all agreed were necessary to address in order to remove that experimental tag from the code base. And these are things like debug tools or CLI options. And today, Bhanu and Aaron are going to talk through the great strides that have been made over the past year to check off each one of these items. They'll highlight how this has improved the usability of OvS-DPDK. So, just before I hand over, we're 1 year on now, and we're discussing the removal of this experimental tag in the near future. Or another way to look at it is just changing the tag around just a little bit. So I'll hand over to Bhanu.
Thanks, Robin, for setting up the context. I'm Bhanuprakash, and I work for Intel. So let's start with the first item in the usability list, the Hues Pages. We did some investigation around Hues Pages to understand how different workloads perform with different Hues page sizes, especially the 2 meg versus the 1 gig pages. The idea was to feed this information back into the documentation. So let's get into the details. Hues pages, as the name implies, are really large pages in the sense they are several times larger than the standard pages. Take the example of the 2 meg page, which is 512 times larger than the standard page 4 KB. And if you take the example of 1 gig page, that's whooping 260,000 times larger than the standard page. It goes without saying that, so that's the reason why the 1 gig pages are called gigantic pages, in fact. It goes without saying that Hues pages are a big advantage because you can fit in a lot more data into the Hues pages. As you can see here, different architectures support different pages, and there are quite a few of Hues pages as well. But our focus has been more on x86-64, and x86-64 supports the 2 meg and 1 gig pages. We ran some micro benchmarking with OvS-DPDK on 2 meg and 1 gig pages to understand how different the performance is with 2 meg and 1 gig pages. What we found out was interesting. There was no big performance difference using 2 meg pages versus the 1 gig pages. Having said that, I should say this is workload specific. This is very much workload specific. And coming to the persistent versus runtime allocation of Hues pages, the Hues pages can be allocated and deallocated at runtime. That means both the 2 meg and 1 gig pages both can be allocated and deallocated at runtime. There has been some doubts with allocating and deallocating 1 gig pages at runtime. I would say that if you have the CMA support in your kernel, that's quite possible. CMA stands for the contiguous memory allocator. With that, you can allocate and deallocate 1 gig pages at runtime because the body allocator as such can't handle 1 gig pages. The next thing in the usability list is the manual pinning of RxQs. This particular example demonstrates the importance of manual pinning of RxQs. If you see here, there is this OvS-DPDK running that does the packet switching, and we have 2 DPDK ports, DPDK port 0 and DPDK port 1, with multiple queues enabled. And we also have 2 PMD threads here, and we have 3 VMs. And VM1 has a pair of vhost ports with single queue, and VM2 has a pair of vhost ports with single queue, and VM3 is slightly different because it has a pair of vhost ports, but it has multi-queue feature enabled. If you count the total number of RxQs here, there are 2 RxQs on DPDK port 0 and 2 on DPDK port 1. That means 4 RxQs here, and we have 2 RxQs in VM1, 2 RxQs in VM2. There are 4 more there, and there are 4 more RxQs in VM3. All in all, we have 12 RxQs, and we have 2 PMD threads. So as you can guess, with out-of-box OvS-DPDK deployment, the 12 RxQs are equally distributed between 2 PMD threads. It's good, but the user is not happy because he really understands the traffic patterns on his particular computes. What he wants to do here is quite interesting. He knows that VM3 is getting a lot more packets, and he wants to isolate the VM3 queues and the DPDK port 1 from the other queues. The reason being, all the packets to the VM3 are coming from the DPDK port 1. That's why he wants to isolate the Rx queues on the DPDK port 1 and the queues on the VM3 to a separate PMD thread. And this is what it would look like. In this case, all the queues of the VM3 and the DPDK port 1 are pinned to the PMD thread running on core 5, and the rest of the queues would be pulled by the PMD thread running on core 4. And this is pretty interesting feature because you can choose and you can manually pin the queue to the respective cores. The next important feature is arbitrary port naming. There has been a lot of restrictions with DPDK port names. As you can see here, if you want to add a DPDK port to the OVS, so the command goes like this: OVS vskettle add port bridge on the DPDK 0. So there is a special convention here that you need to have the DPDK name followed by the port ID. So if you have multiple ports, it will be like DPDK 0, 1, 2, 3, 5, 10. So it's completely meaningless. So from the user, he can't really understand what these port names are. So one has to have a meaningful names assigned to the DPDK ports. And not just that, there is something more to that. And there should be a way that you can understand the PCI address and you can map that to the specific DPDK port. And this particular feature enables arbitrary port naming as well as mapping the PCI address to that specific port. And there is something more to that. So this patch also enables the hot plugging. If you have run OvS-DPDK right now, the funda is like this. You insert the IGB UIO module or the VFIO module, and after that you have to bind your DPDK ports, bind your Linux ports to DPDK compatible driver, and after that you can start the vSwitch. That means if your vSwitch is already running, if you want to add some ports, you have to restart the vSwitch. But with hot plugging feature, you don't have to do that. You can still have the vSwitch running and then add back all the ports dynamically to the OVS. That's pretty interesting feature from the OpenStack perspective. So the next feature is about the auto detection of DPDK. As you know, if you have already installed OvS-DPDK, you would know this. You would first build the DPDK, and then after that, you have to configure the OVS. As part of configuring the OVS, what you do is you have to pass with DPDK and the big absolute path. The reason being, you have the libraries and the header files present in that particular path. So the idea was, if you have the library and the header files installed in the standard paths, why should we use that particular absolute path? So we can just give with DPDK and that should work. This particular patch does the same thing. So right now, if your DPDK library and the header files are installed in the standard paths like the user local or the user, if your library is in user lib or user local lib, and if your headers are in user local or user local lib, you don't have to pass the big absolute path. You can just do configure with DPDK, and you can complete the configuration of OvS-DPDK. The next thing is about the documentation. Last year, if you have seen the OvS-DPDK installation guide, it's pretty big installation guide with 1,000 lines. So this year, what we have done is we want to refactor the documentation. So when we thought we should refactor the documentation, in fact, it's much more than the refactoring the documentation, because when we started this work, we went back to the mailing list, and then we went through all the queries that were posted on the mailing list. Interestingly, 80% of the queries on OvS-DPDK was mostly on setting up the OvS-DPDK, not even about performance and tuning. 80% of the users were struggling with setting up the OvS-DPDK. So we thought the documentation is seriously wrong. So we had split the documentation into two parts. One is the beginner guide, the other one is the advanced guide. So if you're new to OvS-DPDK, I would say you should read the beginner's guide. It's pretty simple, and you should be able to set up OvS-DPDK in no time. And if you are a user who is more into performance, system tuning, and the other features OvS-DPDK provide, you should look at the advanced guide. So there are a lot of things that are discussed in the advanced guide, like the system tuning, the thread affinitization, and where exactly your NIC has to be placed, on which PCI slots, and the jumbo frames, the PDUMP, and a lot of other advanced features. The static analysis. We all know how much programmers love testing, isn't it? So this is for the programmers who contribute code to OVS. If you're sending on the patches to the OVS, I would suggest you should run the static analysis tool first to cover all the corner cases. So what is static analysis? Static analysis is a way of debugging where you would uncover errors just by examining the code rather than executing it. And right now, how it works is you just configure the way that you're doing. Either it is OVS or OvS-DPDK, it doesn't matter. After that, you just run make clang analyze the target. That's it. It would internally invoke the scan build. So this is all part of your Clang static analyzer. And at the end of the day, you would get a very beautiful GUI screen with a big list of errors. And you can go into each of these errors and see where the problem is, and you can fix your problem. So the next thing is about the packet tracing. So this is another important feature that's ranked pretty high in the usability list. So there are two ways that you can do the packet tracing. One is using the DPDK framework. The other one is using the TCP dump. So in the DPDK framework, we have the library and the tool, where the library provides you the APIs to configure the framework and also to enable and disable packet capturing at runtime. So how it works is using the client and server model, where the client would initialize the framework and the server would pass on the information like the ring and the device and the queue that you're interested in. And also, if you want to store all these packets into the PKFL, you can pass on all this information. So that's how this pretty much works. And I would pass on to Aaron to talk about the rest of the features.
Hi, I'm Aaron Conole. I work at Red Hat. So I'm just going to quickly go through the start and stop. We added 2 patch series, one to adjust OVS cuddle so that we can start and stop daemons independently. And the second patch series moved all of the DPDK configuration into the OvS-DB. So now the workflow can be start the database, set your config options, and then start the forwarding path. And then for RHEL, we actually added some systemd enhancements. And you can see in the terminal window, we actually capture DPDK EAL output with the journal cuddle. So moving on, we're going to try and get to a demo really quickly. I'll show configuration of the host, the VM. I'll send some traffic between the two VMs, and I'll do a quick packet dump. So the start, this is a freshly booted system. No configuration has been added to it or anything. So the first thing we would do is configure DPDK, or rather we would configure the host. We would configure 2 meg Hues Pages. We would disable the SE Linux. Well, I'm doing it in the other order, but I'm disabling SE Linux. I'm configuring 2 meg Hues Pages. 6 gigs should be enough, I think, for 2 VMs. Next thing I'll do is I'll start the database, and then I'll dump the other config to show that there's no current DPDK configuration. And then we'll actually set just DPDK init equal true, so just to enable DPDK. And then we'll start the forwarding path, I think. Yeah, so you see the EAL output, and the system is up and running. And now we'll add a DPDK bridge. So we'll set the netdev type to or we'll set the datapath type to netdev. And then we'll configure 2 vhost user client mode ports. Vhost user server mode ports, I'm sorry. And then we can actually start VMs to connect to those ports. And I'm going to use libvirt to do that. So you'll see I verse create first, then the second. Now I'm going to show you just quickly while those VMs come up the configuration for libvirt. So I set the memory backing to be Hues Pages. I set the memory access type to be shared. And then I'm going to actually set vhost user interface type. We'll put it in client mode, showing you the MAC address just because it's going to be relevant. And then we'll actually go into the first VM. And you'll see the ENS3 port. This is what's connected to the vhost user socket that's on that DPDK bridge. I'll configure an IP address, and then I'll start iperf in server mode. Then I'll go to the second VM. Again, log in, configure the IP address, set the, I'll do a ping first, and then I'm going to start a little script. Well, actually, I'll do a client test first, iperf client mode. Then I'll start a little script so that it continually repeats pinging and iperf test. Sorry for my typing very slowly on this, by the way. Then I'll let that go. We'll disconnect from the VM. Yeah, we'll disconnect from the VM, and then we'll do a OVS TCP dump to actually dump the traffic. And that's it, like 4.5 minutes from boot to DPDK.
Thanks, Aaron. So, in summary, we've described the great strides that the community has taken over the past year to improve the usability of OVS with DPDK. And we've focused on it from an OVS user's perspective here, but there's parallel efforts ongoing that enable integration with other layers in the software stack, like OpenStack, ODL. So OvS-DPDK is now packaged by multiple Linux distributions, and it's enabled through checkbox deployment by enabling the integration with the relevant installers. So lastly, I'd just like to thank all in the community who've collaborated to achieve all this over the past year, and look forward to continuing the discussion at the OvS-DPDK Design Summit on Wednesday. So thank you.
Thank you. We're running a little bit behind, but I think that we have time for one question if somebody has one. All right. Well, let's thank our speakers again.